Like to get started now. Right, hands up who'd like to not get started now but carry on nattering and munching. We carry on munching, but not nattering. Okay, the vote's in favour of starting now. So, hi everyone, I'm Mark Harmon, I'm the head of SSE, and we've got two wonderful talks for you today. I just tell you a little bit about the group. So, the SSE group was founded, I think, in 1999, but it was before I came here. So, I think it was founded by Anthony Finkelstein when we moved from City with Wolfgang Emmerich. And software engineering is a kind of really broad church that in some sense doesn't really exist because it's just the intersection of all these other things that you guys are all interested in. So it involves HCI, it involves privacy, security, scalability, networks, large systems, all of these concerns, and really only exist because a group of us care enough about the sort of intersection of all those things to call it software engineering and to meet up and discuss it. But for that same reason, hopefully some of the things we do should be relevant to all these other people because there should be at least one point of contact with one other group in everything we do in software engineering. And so we've selected two talks from amongst our group, both of which we think might have the potential to reach out to other people in the department. And of course the main purpose of these talks is to do just that, to try and present to you things which we think might be of interest to you and you might see ways you can work with us on. So the first speaker is Justyna Petke, who's a senior postdoctoral researcher in the group, and I'm going to hand over to her to tell you about genetic improvement.
Okay.
Thank you.
Hello, everyone. Before I start, can everyone hear me? Yeah, because I'm using the mic. Yeah. Okay, good. Okay, so today I'm going to talk to you about a relatively new area of research that's called genetic improvement. And firstly, I'd like to thank Mark Uwaja, who's a lecturer here, and Alex, who's one of our PhD students, because I'm reusing some of their slides. So I'm going to start with a question. So what does the word computer mean? If you look at Oxford Dictionary, then the word computer means a person who makes calculations, especially with a calculating machine. If you look at Wikipedia, the term computer in use of from the mid-17th century meant one who computes, a person performing mathematical calculations. I want to draw your attention to one common thing here. Computer was regarded as a person at one point in history. Now, who are the programmers? If you go way, way back, these were humans who built Stone Age that's used for, arguably used for predicting lunar and solar eclipses. Moving a few centuries forward, we have Ada Lovelace, who's the first programmer. She programmed on Babbage's analytical machine. Then in 1981, BBC microcomputer was released, and again, you had human programmers who programmed on those computers. Nowadays, the setup looks more like this. So the point of these slides is that programmers have always been people, and loads of them. Now, maybe controversial, but we want to ask why people. Human computers seem quaint today. Will human programmers seem quaint tomorrow in the future? The point is that programming is changing. If you look at the set of things that software developers need to implement, you can divide those requirements into functional and non-functional. Now, functional requirements have to do with functionality of the program. For example, image processing, sound processing, editing functionality. But non-functional requirements are more to do with, for example, execution time, memory, energy consumption, footprint size, and others. We would also like to optimize for. If you look at current software design process, it looks more or less like this. So a customer asks for example, image processing functionality to be implemented. So we throw it at the programmers, and they're quite happy to do it. Now, what if we throw in a few more functional requirements? Then some of them might not manage to, I guess, finish within the time limit, might find it quite hard. Now, what if we ask them to not only implement those functional requirements, but also optimize for memory consumption at the same time? It's quite a difficult task, and some of them might actually give up. Now, what if we ask the programmers to optimize for two more non-functional requirements? And maybe 5 non-functional requirements while still implementing all the other functionalities of the system. I don't think there's a single programmer in the world that will be able to find an optimal solution for this programming software engineering task. Furthermore, there's the multiplicity of platforms. There are also multiple devices that you have to write your programs for. And another difficulty is that the objectives that you want to optimize for are frequently conflicting. So for example, if you want to speed up your software, you might have to sacrifice memory or energy consumption, or both. So how to deal with this? So the question I would like to ask is which requirements actually have to be coded by the programmer, when we claim that humans at least have to define the functional requirements, but we can optimize the non-functional ones automatically. Can it work? Can this agenda work? There has been a study conducted on over 500 million lines of source code, and it showed that you need to write approximately 6 statements before one is writing anything unique. So there is abundance of code out there, and the space of candidate programs is far smaller than one might imagine. Secondly, software is actually more robust than we might think. There was another study conducted on various real-world large pieces of software, and it turns out that after one line change, up to 89% of programs that compiled run without error. This work is by myself and Bill. So the point is that software is robust, so you can make automatic small changes to it, and it will still is going to the task you want it to do. So how can we optimize for those non-functional requirements automatically? And this is where the area of genetic improvement comes in. Agenda for it has been set out in this ASC paper from 2012, so that was the Automated Software Engineering Conference. The Gizmo Challenge stands for Genetic Improvement of Software for Multiple Objectives, and it's co-authored by people from UCL, so there's Mark, Bill, and David, who recently joined from Glasgow, as well as Andrea Arcuri from Similar Research Laboratory, and John Clark from York. So how do we optimize software? Here's the general genetic improvement framework that we've used in our research. First, we start with a software program. Then we may perform some sensitivity analysis. Since real-world pieces of software contain thousands and millions of lines of code, we focus our set of modifications on, for example, the most frequently used piece of code if you want to optimize for efficiency, etc. Next, we apply search to automatically make small changes to the code. And I'm going to go into details about what sort of changes are we making with concrete examples. We have our program, modified it slightly, and then we evaluate if it's still performing the same task on a set of test data. Next, once we have our modified software, we see if it's better than the original. So we have to define our fitness function that will capture what's the non-functional requirement that we want to optimize, non-functional property that we want to optimize. And finally, we end up with we evolve a set of improved pieces of software, and we can choose one depending on our needs. So at the end of the day, we have a software that's improved based on the for the non-functional property of interest. Here's a concrete example. This work was published in the Journal on Transactions on Evolutionary Computation. In this work, Bill and Mark optimized a bioinformatics software for DNA sequence analysis called Bowtie2. And the evolved version that's on average 70 times faster on the task it was evolved to do. The evolved program contained 32 interventions, which were, and we had a post-processing step that, so at the end of the day, we end up with a version that was on average 70 times faster and only contained 7 small modifications to the code. Furthermore, we even achieved slight semantic improvement. And here are the 7 changes. We operated on the level of lines of source code. So essentially, there was a delete, copy, and replace operation. And we also had special rules for conditionals and loops. So, for example, the effect of the first 3 mutations was that the 4 loops, the stopping conditions of the 3 loops was removed. Well, actually, in the 2 cases was removed. So it was replaced with 0 in one case, and in the other case, it was simply disabled. And in the first case, replacement of this stopping condition with this piece of code led to a decrease in the number of iterations for that for loop from over 180 million to 84. And later on, by manual inspection, like the authors of the code discovered that actually this was some kind of legacy leftover code. This for loop really didn't contribute to the outcome of the program, and in a later release, it was removed from the code. And we've discovered this automatically. I'm not going to go into the details about what sort of mutations were here. I'm just going to tell you that this line was replaced with this line was deleted from, so line 766 was simply deleted. This line was replaced with this piece of code, and again, this line was deleted. The overall effect of those 4 changes was that on for certain test cases, the output was slightly better than the original. So, so not only we achieved efficiency improvement, but also slight semantic improvement on a few test cases. And what does, I just want to mention that on the data set that was tested, it reduced runtime of the program from 2 weeks, well, exactly 12 days to 4 hours. So pretty impressive. We've applied the same technique to another piece of software called Barracuda. This work was published at Genetic and Evolutionary Computation Conference last year. And the challenge here was to improve efficiency of another bioinformatics piece of software that consists of over 8,000 lines of code. And it's the first example of where the GI improved code has been adopted into development. So the changes that were evolved have been actually implemented in the system, and since the new version with those changes has been released, this piece of software has been downloaded over 1,000 times, and it's been ported by IBM to one of their supercomputers, and adopted by Lab 7 that provides bioinformatics software to hospitals in the US. One more example that I want to go into more detail is on autotransplantation. Here the setups look slightly different because you start with 2 programs, and you want to essentially transplant a feature from this program into that one. This work was published at the International Symposium on Software Testing and Analysis last year. It won Best Paper Award, well, ICM Distinguished Paper Award. There was also a lot of media coverage on that work, including in the Wired magazine. This article had over 2,000 shares, and on the day where it was released, there was also a news article about Jeremy Clarkson signing a deal with Amazon, and he got more shares on that day than they did. And this work is also covered in BBC Click. So what is transplantation and why we want to auto-transplant functionality from one piece of software to the other? Here's a scenario. Suppose a customer uses a video player and they want a particular video encoding functionality to be transplanted into their video player. Now, what can the programmer do? They can start from scratch, but that's a non-trivial task. Or they can look at, check out open source repositories and see if they can find anything there that could be, they could amend for that particular video player. When then there are over around 100 players to choose from. So again, it seems like it's a quite time-consuming and non-trivial task. Auto-transplantation has its nice analogy to human organ transplantation. That's why I'm going to use the same sort of terminology. So we have a donor program that has the functionality, or in other words, an organ that we want to use and transplant into the host system. In order to do this, we also need to transplant what we call a vein. So the part of the program from the entry point of donor to the organ, so that also the host can invoke the organ within the host. And we also need an organ test suite to see if, well, to test our, for the genetic improvement program, process. So this is kind of the aim. So we transplant organ and kind of a way of getting into the organ into the host. And these are the three, I guess, manual tests that currently need to be done. So we need to identify organ entry point. We need to identify an implantation point, and we also need to have an organ test suite. But that's it. The rest is done automatically. Here's the overview of the MuTrans approach. So in stage 1, we use static analysis to extract organ and the vein from the host. Next, in stage 2, we use genetic improvement, and in particular, we used genetic programming in order to do variable matching as well as extract statements from the organ that we've extracted that actually are needed to pass the organ test suite. So we modify the organ that we've extracted here until it passes the test suite, and finally we implement it into the host, and that's stage 3. Research questions that we want to answer here are: do we break the initial functionality when check that using regression tests? Have we actually added new functionality? So we have a new set of tests that are called acceptance tests that invoke that problem, functionality. And we also measure the computation effort and have a case study to check if it's actually useful. So we performed this following set of experiments. We had 5 donors and 3 hosts, and we simply transplanted the same functionality from each of the donors to each of the hosts, regardless if it made sense or not, in the sense that if we wanted this functionality in the host or not. And then we did a real-world case study when we transplanted the a video encoding functionality into VLC media player. So this is the whole setup. We have a host, we have a donor, we have an organ test suite, and we have the MuTrans approach has been implemented in MuScalpel 2. So you plug these 3 components in. These are automated approach. And we end up with a program that has the new functionality of interest. When it comes to the other experiments, to the empirical data, in 12 out of 15 experiments, we successfully autotransplanted new functionality. So remember, we had 5 donors and 3 hosts, so altogether 15 experiments. And we've also successfully autotransplanted H.264 video encoding functionality from the codec into the media player. And the whole process took 26 hours, which is compared to 20 days of elapsed time that it took developers to perform the same task. And finally, I just want to mention that the tool is actually available online. So if you want to have a go at it, it is there. Finally, I'm just going to quickly go through other applications of genetic improvement. So we also use GI to specialize software for particular problem class. And in particular, we used several versions of software. And then we evolved multiple versions that were faster for particular application domain. We achieved up to 17% in runtime improvement. This work actually was awarded a HUAMI award, which are these are awards that are awarded for human competitive results achieved via genetic or evolutionary computation. We've also used genetic improvement to optimize for memory consumption. And in this work, a multi-objective approach was used, so we optimized both for memory and for efficiency. So we ended up with a set of programs. So the best one was achieved up to 21% memory consumption reduction. And in this case, we used mutation testing to identify parameters within the code that we later modified using genetic programming. So we operated in a more fine-grained level than previously when we operated on the level of lines of source code. We've also used genetic improvement to optimize energy consumption. This work was published at GECO last year, and we achieved up to 25% improvement in terms of energy consumption. And we also used this approach to what we call grow and graph new functionality. So we didn't take existing functionality, we grew something that we wanted, which was a translation feature, and then using genetic programming. And then we used the genetic improvement approach in order to transplant it into the Pigeon chat client. And that work also won the Best Paper Award at the Symposium on Search-Based Software Engineering. So just to reiterate, we use genetic improvement to improve software efficiency, improve energy consumption, something I mentioned, but also port old code to new hardware. That's also been done by our group. Graph new functionality into an existing system, specialized software, and there are also other applications that were also performed by other groups, like bug fixing, for example, has also been done using this approach. As I mentioned before, GI is a very new research area. So the first international workshop on genetic improvement was only held last year. That was co-organized by people from this group. There will be a special issue coming out in the Genetic Programming and Evolvable Machines journal. And there's a special session on GI this year at the conference on evolutionary computation. And given the success of the first workshop, second workshop is going to be held this year during GECO. So just to sum up, within our group, we use GI to add new feature to pieces of software, as we also in Bowtie to improve achieve slight functionality improvement. And we've also optimized for efficiency, memory consumption, energy consumption. However, the range of applications of GI is not yet fully explored. There's been some work on bug fixing, and we also want to target other non-functional properties. So I'll stop here. So thank you. Any questions? Yep.
It's such a wonderful talk, really exciting area.
Thank you.
Well done. So I just have a question in terms of sensitivity analysis. How do you define across what is this program going to be changing? Like, do you, in terms of sensitivity, like, do you just look at like randomly replace different rows, or you have like a way of like parameters across which? How do you define a space of where you actually?
For example, in the Bowtie work, there were the program consists of over 50,000 lines of code that were spread over, I don't remember how many C files. So essentially, sensitivity analysis simply narrowed down the most, most frequently used set of C files. So we modified individual files of C code. So it wasn't the whole code, but just a subset of files that were, I guess, more frequently used. And also in my own work, for me, is that I modified just one file that contained domain solving algorithms. So it's not like we identified, like, I don't know, a method or an object, just one file, for one C file, for example. But again, you could, it depends on, like, there's no, I guess, rule of thumb where how to.
Like you just swap different commands and you try different commands.
Oh, in terms of mutations. No, once we identify the files, then we run the, yes, we usually apply genetic programming in order to modify those files that we've chosen during our sensitivity analysis stage. So, and the mutations are deletions of lines code. So during the search, we pick a line of code and we either delete it, replace, or copy it somewhere else within the file.
Do they have some ground truth to which you compare so that you know that you're like not getting a wrong answer?
Well, the ground truth is the original program. And also we have a set of test cases for the original program. So if we pass the test, I guess we use test cases as a proxy for functionality.
I was wondering about sustainability of code under these transplant operations. I mean, so one reason you might want a human to do it is that they retain beautiful code that's more general and adaptive and all that, whereas if you keep hammering it with an operation that's automated in that way, you might imagine that the code sort of degrades and it becomes harder to do subsequent operations. Yeah. Is that true?
So I have I guess, two answers to that question. Sorry?
Do you want to repeat the question?
I guess it's to do with maintainability of the code and readability of the evolved code. So firstly, because we do those changes in the level of lines of source code, so for example, we can then send to the developers, tell the developers if you just delete this line or replace that line with that line, then you can gain some speed up. So then it can be the developers, I guess, decision whether they want to pursue this change or not. So it's not like they take it as is. And second, maybe more controversial answer is, why do you care? Like if you trust your test cases and they pass your test cases, and frequently, obviously not in safety critical systems, but there are cases where efficiency is more important than correctness sometimes. Also, in terms of, I don't know, energy.
I think you care because
well, that's
you've got a system that you're building up over decades.
I just want to add in.
To answer your question, you say, why would you care? Well, so you make, say, your test cases to be accurate at the moment, but then someone finds a new bug, you add new test cases, you want to understand how you're going to update the software, and if you don't have an understanding of it, if you have software engineers who haven't actually touched this code in a year, and they don't understand how it works, they're not going to be able to go and fix it. I think would be the concern, and that would be the thing that I think.
That's why I have this. This is a two-parter question. In that case, yes, you want to have a nice, I guess, explanation. Well, you simply supply the code, the software developers with the changes they could make to improve their software, and then they can decide whether they want to implement them or not. But there may be situations. Actually, I will give you a concrete example. So, in the software specialization work, I use Minisat to specialize for, one of the domains I was specialized for is the combinatorial interaction testing domain. I'm not going to go into details about the set of instances, but the point is that in CIT you want to devise a set of test cases that's the kind of smallest possible that fulfills certain criteria. And you can encode this problem into SAT and use the SAT solver for this problem. The people don't use it because it's simply inefficient. So in this case, if I develop a version of Minisat that's, I don't know, 200 times faster, but it may degrade in quality, then the point is that the output is easily verifiable. So once we run Minisat and we generate a set of test cases, it's easy, it's very quick to check if it fulfills the desired property or not. So in that case, it would be beneficial to have something that can give you an optimal solution 90% of the time, and you can verify quickly if that's a correct solution or not. Yeah.
So I guess related but unrelated. Does your code generation or whatever you use to pick which lines you insert, does that respect like the C secure coding standard if you're doing C, or like do your test cases cover you injecting bugs, or like how do you make sure you're not making the security of the code worse as you evolve it?
Okay. The reason, the way we, okay, I guess the short answer is no, we don't care. But we do care a little bit. We have this what we call BNF-like notation. So kind of like a BNF grammar. So for example, we don't touch the lines of code that are simply initialization lines of code. So, and the brackets as well kind of are left in place. So there are certain rules that we stick to, and we prevent those lines from ever being modified. And also I mentioned the special rules for conditionals and loops. So we don't, a pen would be useful. There's no pen, okay. So we don't actually replace the whole line with a for loop. So you have for and, I don't know, some start condition and iteration, it consists of 3 parts, or maybe even simpler an if statement. So instead of moving this whole line, we only allow to replace this part with another if condition from somewhere else in the code, for example. Or just completely remove it, replace with 0, stuff like that. So we have some rules to kind of thank you. And because of these rules, I guess, I should mention that the compilation rate that we had in our experiments was 80%, so it's pretty high. About 70-80%. Yep.
Sorry, it's another one. Taking an analogy from organs and transplants, do you need to test whether the host is compatible with the organ that's coming, or any organ is on?
That's kind of why we kind of picked, did the transplantation between the 5 donors and hosts, kind of, we did all those transplants, so we didn't care about whether certain functionality made sense in the donor or not. We just want to see if we pick some functionality from one donor and compare it into a host, if it's feasible or not.
So you do 20. You don't check if the host can tolerate that particular function.
Oh yeah, sorry, I misunderstood your question. We use test cases. We use those acceptance tests to see if that functionality can be invoked in the host and if it does what it's supposed to. So we use testing.
Follow up on that. I was going to suggest that you can call that when you're doing heterologous transplant or something is a donor to something that you can transplant from the same code to the cell itself. So that when
Yes.
you're autologous, so if you name it that way, you can actually, in the autologous you don't have to check whether the donor and donor is the same thing. And heterologous is the case you thought is heterologous. The donor is something different than
Yeah. Actually,
needs to be matched, and therefore needs to be matched.
Yes, exactly. As a sanity check, in one of those 15 experiments, we transplanted from C-flow to C-flow. So something from the same program, so we extracted that, and then we kind of transplanted it again. And in all 20 experiments, this was successful. So it was kind of a sanity check there already.
But in that case, you don't have to check compatibility because
Yeah.
autologous.
Yeah.
So how close are you to, if you use MATLAB, I use it all the time, and so it's what I'm familiar with, but it will give you suggestions as you write code. It says, why don't you do this instead because it'll be faster. How close are you to being able to use these systems in real time?
Real time. Not close enough, I guess. It takes It takes hours to days to run the whole thing, but just thinking like, but the thing is we produce like thousands of variants already, and yeah. Now to get an improved version, you really can't really say when you're going to get it. It may happen like within first generation in the GP approach, you're going to have something very quickly, but yeah, I think it's not yet real-time ready. But there is, sorry, I should mention that there is work on embedded online genetic improvement. So other research groups have, let me give you an example. That was used for software slicing. So a group from INRIA, a French institute, they developed a tool when they so they embed the GI framework. So they have a framework that's used as GI approach for software slicing. So it can do the changes as the program is run.
Okay, if there are no more questions, let's thank Justyna. So we're going to have a 10-minute break now so that people can avail themselves of sandwiches and so on. And also I think some coffee has arrived, which has been very restrained. And then we'll have a talk by Emmanuel. Thank you so much, Justyna. So it's a bit cold in here, so I hope everyone has a chance to warm up and shake them back and all that sort of freshness back. Right, so our next talk, so not everything we do in software engineering is all about the code. There are lots and lots of other things in software engineering, and one of those is, good luck with that. And one of the other things is to do with the other end of the spectrum, so the requirements of how we decide what it is that goes into the software. And Emmanuel is far too modest to say so, but he's one of the world leaders in this area. And in fact, this year is the program chair for the main international conference in this topic. And he's been working on techniques that allow us to quantify the value of information, and when we try and reduce uncertainty in information, how to quantify that. And I thought this is something that might actually have applications outside of software engineering. So I'm really grateful he's going to give a talk about that.
Okay.
Now, and we'll see if there are.
Okay, thank you, Mark. So yeah, I will talk about value information towards the end of the talk. I first want to step back and give a broader context of what software engineering is about. And the current trends we see in software engineering, but also in society. And one thing that we see is that increasingly innovation is driven by software, in all sorts of sectors, in healthcare, in automotive, and so on. And there's an increasing number of companies who invest a large amount of their research and development funds in software, even though they're, for example, building cars or other kind of mechanical things. The largest portion of research is in software. And one thing is that, in the 20th century, a lot of the software engineering projects were about automating manual processes. Okay? And they kind of assumed that we could know the requirements up front, these were relatively stable, and we could build systems from these stable requirements. And when you've got stable requirements, we know how to do it. Now we've built the techniques that we know how to write code and test it and do this. This is no longer a challenge. But what happens today is that most software engineering projects at the moment are not so much about automating things that already exist, but it's about changing process, changing how we do things, changing how we deliver healthcare, completely changing how cars are being driven, completely changing lots of different aspects. And so it's about innovation, changing the way things are done, but this also entails that it's much harder to know upfront what you need to build. So there's much more experimentation going on. Software engineering is now much more about experimenting and trying to find out what you need to build. And at the same time as this happened, what happened is because there's an increasing number of software everywhere, it generates much more data. As you're all aware, everyone's talking about big data. And the fact that all this data enables us to try to better understand what the needs are of the different people using software or different people in society. And by better understanding these needs, we can further innovate. And so there's a kind of virtuous cycle there. And a large, a portion of the software engineering research is about, how can we strengthen this loop? Okay, how can we make these loops better? So we can generate a lot of data, but then from the data, understanding user needs, this is something that a lot of companies are trying to do, but it's not that easy, and not everyone is able to do it, and that is able to make that work, going from the data to having useful understanding of what people want. And there's some research being done in the group where people, for example, are analyzing reviews in app stores to try to understand better what people using mobile phone applications need. And so that's one example of research being done in software engineering, where we're trying to go from strengthening this arrow there, but we'd like to be able to do this much beyond App Store and mining review, but understanding the way people work and do lots of things so that we can better understand their needs. And once you've understood their need, another big problem is how do you translate that to innovative products? How do you design the right system that will help address these needs? And this is a large part of the research that I do in requirements engineering is about translating needs to innovative product that makes life easier or better. Okay. And another thing we see in software engineering, at the same time as we've got this loop here, we've got a negative loop on the other side. So because we're building more and more software, the software grows both in size and complexity, and people have estimated that that every 5 to 10 years the size in terms of lines of code grows by an order of magnitudes. And this means that as soon as we build tools and techniques that can handle the complexity that we've got at a moment in time, about 5 to 10 years later, it no longer scales. So one example is Facebook that was using Git for its version control system, and a few years ago they found out that Git would no longer scale to the amount of to their source code and the amount of commits they had, and they've moved to another version control system that they've had to upgrade. And so there's lots of techniques that we need to improve all the time to be able to maintain this innovation. So we're trying to strengthen this loop here, and we're trying to weaken this one. Okay? That's what we're trying to do. And a lot of software engineering is about making decisions. We need to do lots of decisions while we build software. It starts from people within an organization deciding what IT projects they will need to fund, or they will decide to fund, and which one they will not fund. Once they decide to go for a project, they need to decide, okay, what kind of function do we want in that software? What kind of qualities do we want? What level of security do we need? What level of reliability? What level of performance? And so there's lots of questions there. From there, they also need to decide what architecture do we need? What kind of architectural style? What kind of components? What technology are we going to choose? There are lots of decisions to be made. Then when people start coding, they need to decide what design patterns are we going to use, what data structure, what algorithm, all this kind of code level decision. What testing are we going to do? How much testing? What caused the bug? How do we fix a bug? And then when software is in use, how and when should we change the software? Okay, so there's really a lot of questions. These are probably the main one, but there are others. And we can probably classify them in two different kind of broad kinds of questions. One are the strategic business decisions that are basically about, should we fund these products? Okay, you're in an organization and you want to decide where you want to invest your money into the development of innovative software. And this is basically, you've got a very few number of very big decisions. Okay? And the kind of technique people used to do that are typically the kind of thing that people who studied in business school would use technique from decision analysis to do this. Okay? And at the bottom, we've got code level decisions. So, what kind of data structure you're going to use, what algorithm, what you're going to put in your if statement, and so on. And here we've got an extremely large number of small and local decisions. And this is where techniques like genetic improvement and other search-based software engineering technique that the group is working on, we're dealing with these very large number of decisions at the code level. Okay? And the thing that I'm interested in are the decisions that are in between these two, typically decisions about requirements and architecture, where there you've got dozens of key decisions that are hard to change. Okay? And they sit a bit in between these two. And so to make concrete, I'm going to give an example. So this is an example of a system where we studied the scalability of a financial fraud detection system. And this was part of the PhD thesis of Laetitia Duboc, who worked also with David Rosenblum. And so it's a company in London that develops financial fraud detection system for large banks. And their question is, will our system scale to the increased volume of transactions? Banks were merging at the time, and they were worried their system would scale. And because the question they have is, should we build a new system or not? Okay. And if they build a new system, eventually they did build a new system. What are the requirements in architecture for that system? So, and the example of question would be, what kind of processing are we going to do? Are we going to do batch processing because their current system was processing transaction in batch overnight, or should they move to a continuous processing of the transaction? The kind of detection method, should they use rule-based detection? Should they use a statistical classifier or a mix of these things? Also the blocking policy, should you block first as soon as you detect a possible alert? Should you block the card or should you investigate first? And so there's lots of decisions. There were a few decisions like this for the system. Okay? Okay. And characteristics of these decisions at the requirements and architecture level, and possibly lots of other, is that uncertainty is inevitable. Okay, it's hard to know, what are the stakeholders' goals, and you may have uncertainty whether you've identified the right goals. There's uncertainty about what are our options, what are the decisions we should take, and for this decision, what are the possibilities from which we need to choose from. And quite importantly, it's very hard to know precisely what the impact of each of your decisions will be on the stakeholders' goals. Okay? If you move from batch processing to continuous processing, what impact will it have, for example, on customer satisfaction or on your ability to prevent fraud? Okay? So we've got uncertainty there. And also, there's uncertainty because often you need to make this decision by kind of anticipating what the business will be in the future. For example, how can you anticipate the growth in the number of transactions in 5 or 10 years? Okay? And so when you're dealing with software architecture decision, you must decide, but you must decide without having all the information, or without having perfect knowledge about the problem. Okay. And in software engineering, there's different approach to deal with uncertainty, and one that's very popular at the moment, especially in industry, is the one I would call the surfer's approach to uncertainty. And the people who promote, so for example, there's a consultant called Marie Poppendieck who gave a keynote at ICSI called Learning to Surf, where she explains that approach that basically, because all of these decisions we need to make in software engineering are so complex, there's no point in trying to plan everything and trying to model the problem. It's not going to work. It's much better to trust your instinct and be adaptive. Okay, be like a surfer and go with the flow rather than trying to plan. And a lot of people, including academia, tend to think that this problem is too complicated to be dealt with in a mathematical manner. We should just go with the flow. Okay. Then a second kind of approach, and that's the kind of approach that you would see lots of research papers about. It's also the kind of approach that you would see in professional handbook about software architecture, about project management, and so on. It's an approach where the difference with the surfing approach is that there you try to identify explicitly what criteria you want to use in making your decision. You also make a list of the decision you need to make, okay? And then you use a numerical approach where the problem is that the criteria that they use for decision are numbered without verifiable meaning. So for example, you'd say, what's important for my system is to be scalable and also security. And I would say, for one system, the scalability is at level 3, and the security score is 5. Whereas another system, for example, scalability will only be 1, and security would be 10, for example. But you don't know what these scores mean. Okay? It's a bit like university ranking or all these kind of things. You've got numbers, but you know there's some magic formula that computed them, but you don't really know what it means. Okay? And the problem is that the decisions model are not falsifiable. Okay? And there's lots of techniques that work that way. And what I'm trying to do, and others are trying to do in research, is to have a scientific method for making these kinds of decisions. Where what we want to have is to have measurable decision criteria. We want to have falsifiable decision model, that the equations we use for making are falsifiable. We can test whether they're wrong or right, and we can possibly improve them if we see they're not good enough. And we model uncertainty as Bayesian probabilities, because not only one of the advantages is that it allows us to combine hard data with subjective beliefs, because we can't always have all the data we want. And also to use a principal approach to multiple objective optimization. Okay. So, what do we mean by uncertainty? So, I've got a next slide where I spent a couple of minutes explaining this, and it's probably very basic, but I've seen in the past that if I don't do this, people get confused and ask me questions about what, saying that they disagree with me about what uncertainty is and so on. So I prefer to give the definition, even though it's a bit obvious. So uncertainty, it's obvious when you see it. So uncertainty is the lack of complete knowledge about a state or quantity. So you're in a state where there's more than one possible value, and the true value is not known. Okay. So I'll give two examples here. So one thing is, will the UK leave or remain in the EU after the referendum? We've got uncertainty. Okay, it could either leave or remain, and we don't know at this stage. Okay. Another question is, when will the department move to a new building where we're all together? Okay, that's another state of uncertainty. Okay, and an interesting mathematical insight is that it's possible to measure uncertainty. So there's not just these two states, but also we can measure uncertainty by, for each possible value, giving a probability of what we believe is the likelihood of these things happening or not. So, for example, will the EU stay or leave? If you look at the betting agents at the moment, they believe that there's a 1/3 chance that we leave and 2/3 that the UK remains in the EU. And when will the department go to the new building? My 90% confidence interval is sometimes between 2017 and 2050. We're looking somewhere 25 or 30, I don't know. And each of us could have a different uncertainty here, but we do, even though we don't have hard data, we have a belief about when it's likely to happen. Okay, so it's possible to measure uncertainty that way. Yes.
Which betting agent is taking bets on when the CS is moving into a new building?
You can go on Betfair and create your own bets.
Fantastic.
Yeah. Or you can create one in the department. That would be an idea. And okay. Okay, so that's about uncertainty. So the technique we apply for is decision analysis, and I'm going to describe very quickly and briefly the decision analysis cycle we go through, which is classical. It's the thing that people who study in business school learn. How you make decision under uncertainty. You need to model the decision problem, means identify what are the objectives of your decisions, and what are the different alternatives, and you build a model that describes how the different alternatives affect these objectives. Okay. Then, because these models rely on parameters, and these parameters are usually uncertain, people don't have perfect knowledge of this, you elicit what the decision makers already know. So before you've made any measurement, you ask people, okay, what is your uncertainty, for example, about the department moving to the new building? Okay? And this gives you the prior probability distribution, what people already believe about the world. Then from this, you can only shortlist a set of alternatives. That means that some alternative you can already, from what people already know, you can already exclude all of these alternatives, and you've got others that you can keep. And typically, what we will do here is we would keep the set of Pareto optimal solutions with respect to our objective, given our current uncertainty. And then the thing is, you want to think about, do we need more information before making a decision? And this is where you can use a concept that I'm going to talk about a bit later called the expected value of information. Probably some of you know it, to decide whether it's worth doing more measurement or more analysis before making your decision. If the answer is no, then you finish, you pick one of your decision and you start implementing it. If it's yes, then you start gathering the data that will help you make better decision, or start doing some analysis or prototyping or whatever needs to be done to get more information. And this kind of revise your model, revise the probability distribution, and then you continue. Okay, that's the idea. So as a kind of high level, to give you the intuition, so for example, for the financial fraud detection system, the bank goals are things like you want to minimize financial loss, so the loss that the banks incurs because of fraud. You also want to minimize the fraud detection costs, because some human fraud investigators are involved as well, and you want to minimize that. And they also want to maximize customer retention. Of course, there are other stakeholders with other goals. The company developing the software, what they want is maximize their sales to the banks. Okay? And decisions are the ones I've listed here. So, for example, rule-based or classifier. But you also want to decide the threshold for some of these. You want to identify parameters for some of these methods. For example, the threshold at which you generate alerts. What's the best trade-off between false positive and false negatives on this system? And then you also have lots of model parameters, like the number of transactions per day, the growth rate for this number of transactions, the fraud ratio, the alert investigation cost, and so on. That you need. Some of them you need to estimate. Others you can look at data from the past and have kind of more precise knowledge about. Okay. And so at the moment we've done this kind of analysis using R, and the idea that we have at the moment is to be the tool to make this kind of analysis easier for software architects and also people in other domains. And tool basically looks like this. People need to write a decision model and elicit uncertainty. This goes into the tool that would perform the multi-objective optimization and Monte Carlo simulation. Monte Carlo simulation to analyze all alternatives, and then multi-objective optimization to select the best one. And this gives you a short list for your best solution, and some kind of risk analysis as well. And from there, you can also do the information value analysis to identify what model parameters you would need to get more data from or more information from to improve your decision. Okay. So in terms of current research, so these are 3 PhD students who are working on this topic at the moment. 2 of them are in the back. So Said is working on the tool for improving decision in goal-oriented requirements model. Olawole is working on how to take into account financial consideration when you're doing software architecture decision. So things like cash flow, net present value, which is something that people care a lot about when in lean software development methods. And David Stefan, who started with whom we started this sort of thing with Earl, has been working on environmental sustainability at Ashler organization, and he's done notably case study with UCL estates to apply these methods. Okay. So quickly, expected value of information is. I'm going to talk briefly about it, and it's more a teaser about what the concept is rather than really a full introduction to it. So the idea is that, if you recall, initially decision maker can have large uncertainty about the parameters in the model, and so the problem we want to address is what additional analysis or measurement should we perform to improve the decision, if any. Okay? And the idea is that you should perform additional analysis only when the expected value of perfect information is much bigger than the cost of analysis. Okay, there's no point trying to starting to measure things if it's not going to improve your decision. And the expected value of perfect information for a parameter x in your model, as a rough intuition, okay, then you can look at the paper there or in a decision analysis book for the decision, but as a rough intuition is the expected increase in goal satisfaction that are measured in pounds or other monetary value if given access to the true value of x. So in the hypothetical, theoretical case where you could pay an oracle to give you exactly the true value for that variable, what would it be worth to you? How much would it improve your decision? Okay, and obviously you should not pay more than that. Okay, this is a maximal for what the information would be worth. And the reason why it's useful, why that measure is useful, so some people have applied these techniques for strategic IT decisions. So we've got people present business case for IT projects, and then should the company invest in that project or not, based on the cost, but also most importantly based on the value that the project will bring to the company. And so someone called Douglas Hubbard applied this for more than 20 business cases, and what he found that most variables in his model had between 40 to 80 variables, and most of the variables have zero information value. So if you start from what decision makers already know about the variables, most of these variables, there's no point in trying to get more data, reduce uncertainty about them. And the thing is that variables with high information value were typically the ones that the clients never measured. Okay, and typically these were things about the impact that the IT system would have on improving efficiency for the employee. So typically, a lot of things relate to the value of the IT system. This is typically viewed as something purely qualitative that you can't measure, and so people didn't measure it, even though it was the most important to their decision. Okay? But on the other hand, the client spent most of their effort measuring quantity with low or even zero information value. And the examples are mostly variable related to cost. So they wanted to measure precisely how much time people were spending on each activity. If you've worked in some company where people ask employees to keep timesheets and all these things, they wanted precise information about this, even though it was not useful for their decisions. Yes.
Do we do the same when we assess students?
Possibly. Yeah.
Could you apply this to understand how better to structure an exam system so that we only assess students?
I mean, once you've got this in mind, you kind of feel that there's so many places where you could apply it. And I was thinking you would ask it about the ref, because that's another example where there's lots of measurement, very precise measurement about things, and where does it change anything?
Other universities are already offering you money to give them information that's of virtually zero value for their next rep, but they're still happy to pay for it.
Take their money, Mark.
Yeah. And so there's this comes to, so Douglas Hubbard said there's a measurement inversion bias or paradox, where basically the less something matters, the more we measure it, and the more something matters, the less we measure it. Okay, and that's a pattern that you can observe in lots of places. And I think the reason for that is that basically we prefer measuring things that we find easy to quantify and already know a lot about. Okay, think about in your research, if something is easy to quantify, you would put that in your results section. Whereas things that matter are often hard to quantify, and we know little about them. Okay, and therefore, the thing is, when we already know a lot about something, reducing uncertainty about it generally has very little value. Okay, whereas something that we know little about, if we can reduce uncertainty even just a little bit, then it can have a big value to your decision. Okay, so for example, what's the value of building the software to the on the productivity of your employee? It's something hard to measure because you haven't even defined yet productivity and so on. So you need to do a bit of work there. But if you can reduce uncertainty about the effect of different systems on this, then it can have a high value. Okay, and of course, the question Mark anticipates is does this kind of pattern apply to your research area? If you look at the empirical results section of some of the research papers in your area, do people can tend to measure the wrong things basically? It's food for thought. Okay, so I don't want to take much longer. So basically, as a conclusion, so the main message for my talk was that innovation is increasingly driven by software. I don't need to convince you in the computer science department about that. And decision under uncertainty is fundamental to software-driven information. And my research hypothesis is that having a Bayesian model-based approach will lead to better decision than using intuitions. Okay? And because it's a departmental seminar, I also want to end with the last slide talking about, where I will try to see what kind of possible collaboration could exist with other people in the department or elsewhere. And typically, so one thing you could see, so this work is about the software engineering and the strong relation with modeling, optimization, and machine learning. So typically, we use, in software engineering, we use optimization methods to find a Pareto optimal solution, and inversely, software engineering techniques are quite important for people who build software that deal with optimization. So, for example, if you want to optimize bed allocation in a hospital, if you want to optimize healthcare process, it's not just about the optimization algorithm. You need a full software that deal with all the aspects of the system. Similarly, with machine learning, there's lots of work in software engineering that use machine learning to try to understand better what software to build or how to build software better. And conversely, software engineering techniques have a big role to play in the development of machine learning system, not just the algorithm system. The example, for example, was the financial fraud detection system. It's not just about the statistical classifier. It's all the software that goes around it needs to work together with the classifier. And of course, this technique can be applied in lots of different areas, like healthcare, security, embedded systems, and so on. Okay. So I'll finish here.
I'm not certain if there are any questions, but one way to find out is to ask my data, so reduce the uncertainty there.
So you talked about how when you're trying to find some candidate alternatives, you shorten yourself down to a Pareto optimal list, and you're doing this via multi-parallel simulation. So are you using sort of game theory and decision theory in order to make decisions in this space? Why? Could you talk a little bit more about sort of how you're making that, doing that decision making, and why Pareto optimality is used?
Okay, why Pareto optimality? Well, it's because typically most of these problems have multiple objectives. Okay, and in the context of multi-objective, there's basically two approaches. Either you do the Pareto optimality, where you accept there's multiple objectives and they might be conflicting, and Pareto optimality allows you to explore the trade-offs between these multiple objectives. And I tend, and other people in the group as well, tend to prefer this approach as opposed to the other approach, which is to kind of trying to reconcile these multiple objectives into one objective by typically assigning weights to the different objectives and then computing the weight of sum for the different objectives, typically as a utility function, if a single utility function. Okay, where the problem there is, where do the weights come from? Now, the thing is, in practice, sometimes you cannot have too many objectives because the decision becomes too difficult, and sometimes you need to combine these objectives. But I really feel strongly that when we do this, we should try to always identify a goal that corresponds to something that's measurable, as opposed to using weights where. But you could use kind of weighted sums if you prefer instead of Pareto optimality.
More questions? More questions?
So, I have to admit that I actually have read some of the papers that you're talking about. There's so with software, decision theory models the world as if nature makes a choice and then you make your choice. So there's only really one player. Have you looked at all at the stuff for generalizing the expected value of information to when there's an adversary? Because that sort of changes the math for security.
Yeah. I mean, that's a very good point. So I have to say that this is the beginning of applying decision analysis in software engineering. There's not many people who've done this. It's really the beginning, and that's absolutely something that we should look at, and especially as you say, in the context of security, but also in the context of company. So typically startups, we also need to think about what their competitors will do, and so kind of moving. That would be another kind of future work that would be very interesting. Yeah, maybe a future PhD thesis. Yeah, good point. Thanks.
What happens if one doesn't know which are the important questions to ask? I mean, you classified the questions in those with high and little information value, but there is also some uncertainty in how to do this classification.
Okay, so what happens if you don't know what question?
I mean, you presented this trade-off, and you said there are some things you can measure very well, and others you can measure less well, but they are more important to know.
Yeah.
But still, this classification, if you take REF, for instance, often is not so easy to come up with in the first place.
Absolutely. So the question is, what if it's difficult to identify what matters, basically?
Yes.
Okay, and so. And that's precisely why you need people who are expert in asking questions to identify what people actually want to achieve. Okay, so when you've got a decision problem, what you need to first do is identify who are the stakeholders in the decision problem. There's usually there's more than one group. There's a lot of groups, and for each stakeholder, you need to identify what their concerns are. Okay, and the problem is that some people start with a defeatist mind where they believe up front that it's impossible to identify what the concerns are, and even less to reconcile them or to measure them. But you need people who have been trained and know how to do this, and the REF is a good example. If you start to have a meeting with people responsible for the REF, asking them, well, what do you actually want to achieve in the end with this REF exercise? The beginning of will be a mess. People will disagree. They will not know. But then you need a facilitator to help them, pick up all the different issues and come up with, what is it they want. Possibly, if the UK being seen as a leader in this and that, but also have a fair allocation of money across university, and how do they measure fairness? How do they measure the UK? And it's possible to do, but you could have it wrong, but the benefit is if you make these objectives explicit, then people can start criticizing them and say, well, you're also missing that other objective, or this objective is not the right one, and then it can improve. Whereas if you leave them completely implicit, you can't improve the decision process at all. Yeah. I'm sure you know. Yeah. Yes.
How do you make better questions when you're using data to improve the questions? In the loop that you started at the beginning, how the intense data is used more to find out what matters. Yeah.
Okay. Yeah, I mean, that's a very interesting question. Because typically, we build software and then we collect all the data we can. We generate lots of data, we collect them, and then we've got a vast amount of data, and then we don't really know what to do with them. We try to find correlations and so on. And so a lot of the kind of research and the way people do things here is basically data-driven. We start from the data and then we try to see what we can do with it. Okay? Whereas this kind of decision analysis approach is more goal-driven. You start with, okay, what do we want to achieve in terms of goals? What are the decisions we need to make? And from these decisions, what data should we collect? So you kind of derive the data you need to collect from the decisions you want to make and the goal you want to achieve. And an example of this was David Stefan doing the work for environmental sustainability. So he did one case study for UCL Estates where their decision was about, so UCL has a combined heat and power generator, and it's a very old machine, and it's used in this building notably, and they need to decide when they switch it on and off, because for some reason, I don't know, they cannot switch it on and off easily. And so they switch it on at certain dates in, I don't know when, I think it's in October or something, and then they switch it off at some other date. and they figured that they could save some money by changing the time and so on. But they decided that, well, in order to make a good decision, they thought that they have to fit lots of UCL buildings with meters to understand energy consumption much better. Okay? And so basically what Stefan does, he modeled the decision problem, and using information value, he showed them that actually, these meters were completely unneeded, because with the information they already had, they knew they could make the decision, and the additional information from the meter was completely unneeded. So basically, it saved time. It saved them money and time. The money for installing the meter and the time they could make the decision faster because they didn't need to buy the meter, install them, collect the data, and so on. Yeah. Is that?
Well, yes and no. This is a real problem that I have with my research. I'm doing experiments on behavior change and it's a big data approach. We're doing a series of experiments that they need to change from one iteration to the other depending on what's happening with the previous user tests. And we have an idea that we want to help people improve. But let's say on fitness. But then you say, what is that? Is it that walking more, jumping more? And we really don't know until we throw the problem to the users. They react, they generate data, and they say, okay, it's a problem for data. So you start a process in which you want to find the questions that matter, but the question itself causes to be evolution. So I just wonder.
Yeah. I mean, that's possible. We can have a discussion about that afterwards. Yeah, you could. I've got a suggestion of what you might do. Typically, identify what the stakeholders are for your problem, and think about them, and from there derive the measure. We could discuss about understand the problem better. Okay.
Okay, let's thank Emmanuel. Thanks very much, Emmanuel. So, thanks very much everyone for coming. If you've got any decisions to make, some information that you need the value of, or some transplants or software you need improved, you know who to talk to. Thanks very much to Sarah for organising. What's next month? So next month is going to be Media Futures, telling you all about their research. Thanks very much for coming. That's why it's all your fault.
That's the air conditioning.
That was a great thought.
Okay.